There is no way to get through complex numbers, either in a class or in your own self-learning, without getting through polar coordinates. Now, it is one of the most useful, interesting, and impactful tools you will be able to use when it comes to answering questions that involve complex numbers. So we'll talk about both polar coordinates and Euler's formula in this video of Complex Numbers 101. When it comes to polar coordinates, we need to first describe what they are visually, or geometrically if you prefer. So let's start by having a complex number here. And when we talk about polar coordinates, it is now a change to its distance from the origin as well as its original angle. That's what polar coordinates will be a part of. We'll write that up here. We'll say its distance, its radius, and theta, its angle from the x-axis. So, when we want to try to convert z in standard coordinates to polar coordinates, this is how we do it. So we need to change it so that x and y x plus I times y can be rewritten to involve something involving its radius from the origin, its distance from the origin, and theta. So let's start by figuring out what the radius is. So before, in our previous video about complex numbers here, we talked about the modulus and how it was in fact its distance from the origin, which now we are going to use as r. So we know the modulus of z is related to r here. So that's great, that's one coordinate down. Now we need to figure out theta. So using the right-hand triangle, the distance in the real and imaginary parts we know is x for the real parts and y for the imaginary parts. So using SOHCAHTOA involving right angles, we get two new equations. We get that cos of theta is equal to x over the modulus, which we said we were rewriting as r, as well as a second equation, which is sine of theta is opposite over hypotenuse, which is y over the modulus, or y over r. So what that means is now we can rearrange these two equations to get that x is equal to r times cos of theta and y is equal to r times sine of theta. Now, for those of you that knew about polar coordinates when it came to real numbers, this is very nice to know that these equations still hold for complex numbers. So now let's take these and sub it in for our x and y here to get our new polar coordinates for a complex number. So z is equal to r times cos of theta plus I times r sine of theta. So now we get our final version that z is equal to r times cos of theta plus I times sine of theta. And that is how the polar coordinates were made for complex numbers. Next, we need to talk about Euler's equation, because this was a very important discovery. And what his equation stated is that if you took e to the power of I times theta, this was the same as writing cos theta plus I times sine of theta. Because this is such a fundamental equation we use involving complex numbers, this is worthy of two proofs. The first is going to be for those of you that are familiar with power series. So the fact that e to the x can be written as the sum of n equals 0 to infinity of x to the power of n over n factorial, as well as cos of x can be written as the same equivalent a similar sum to this with only the even terms for it. So this is equal to 2n factorial over x to the power of 2n, where it is alternating between the two. And then finally, sine of x, which is the alternating odd terms. So we can write the first few terms of the first one as 1 plus x squared over 2 plus x cubed over 6, etc. The next one is the alternating even terms, which is going to be 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial, etc. And the final one, which is x minus x cubed over 3 factorial plus x 5 over 5 factorial, etc. So cos basically includes all of the even x exponents, and sine includes the alternating of all of the odd ones. So what happens is when we take these and use them now with complex numbers, we get the following: that the power series breaks down to become I to the power of theta times n all over n factorial. So now when you break this up into particular cases, you get the sum of all of the even terms, which is I theta 2n over n 2n factorial, plus the sum of all of the odd terms, which is I theta 2n plus 1 over 2n plus 1 factorial. And what happens is that we know that for each of the even terms, the I gets squared and becomes minus. So we get a minus in front here of all of the even terms. Specifically, minus 1 is the power of 2n, so we get minus 1 to the power of n. But when we take out an odd one, technically I gets squared, so we get a minus 1 times n here, but then we also get an I in front, which I will leave over here. So now the I is gone in both of these. We see we have an alternating series of cos with nothing in front, and we have I times an alternating series for sine. So in fact, this is equal to the power series of cos to the x, and this is equal to the power series of I times sine of theta. And that's how it was discovered using the power series. Now, in my opinion, a way cooler way of showing this was actually using derivatives. So if we let f of theta be a function that is the right-hand side divided by the left-hand side. So we'll say cos theta plus I times sine theta all over e to the I theta, which we can quickly rewrite as e to the minus I theta times cos plus I sine theta. If we take the derivative of this function, we will get that the derivative of the first is minus I e to the I theta cos theta plus I sine theta times the derivative of the second, which is plus e to the minus I theta times minus sine theta plus I times cos of theta. So now what happens is that if I take this side and take the minus I and I bring this in, I will now get e to the minus I theta times minus I cos theta. I will get minus I times I, which is minus 1, so I will get plus sine of theta plus e to the minus I theta times minus sine theta plus I cos theta. Which you will notice these are the opposite sign, and the signs are the opposite sign. So this whole thing is equal to 0. So now, what they found was if from your high school, you would have known that if a derivative is 0, we know that the entire function must be equal to a constant. So this whole ratio is equal to a constant. So if I now plug in f of 0, we know that every value of this function must be the same here. So cos of 0 is 1 plus I times 0 all over e to the I times 0. Times 0. So since sine of theta is 0, there is no I in this, and since e to the power of 0 is just 1, this function is always equal to 1 for every single value of theta. Therefore, this is equal to 1, which then implies multiplying by the bottom, e to the I theta is equal to cos theta plus I times sine theta. And that, in my opinion, is one of the coolest ways to prove Euler's equation. Finally, we can now showcase what I like to call the final form of polar coordinates. So, using Euler's equation, as well as what we did in the beginning of the video, which was show that z is equal to r times cos theta plus I sine of theta, we now get that the final form of polar coordinates is z is equal to r times e to the I theta, where r is equal to the modulus of z, which is the square root of x squared plus y squared, and theta is equal to the tan inverse of y over x, where x is not 0. Like and subscribe if you want to see more. And please feel free to comment if you want to see a topic that involves complex numbers or other forms of math. We have tons of other playlists on this channel involving all high levels of math. So if you're looking for help, this is the channel for you. Until next time.